For centuries, physicists believed the universe followed a simple aesthetic rule: symmetry. If you flipped the universe like a mirror, the laws of physics were supposed to work exactly the same way. Left and right, up and down, it shouldn't matter. This idea wasn't just philosophical. It was treated as a fundamental law of nature. And then, in the 1950s, one experiment proved that belief was wrong.
Behind every moment lies a scientific wonder. I'm Kale, and welcome to SciCurios, where curiosity meets science.
At the center of that experiment was a physicist named Chien-Shiung Wu, who was born in 1912 in a small town near Shanghai, at a time when higher education for women in China was rare. Her father, unusually progressive for the era, founded a school for girls and encouraged her interest in science. That early support would shape one of the most important experimental minds of the 20th century. Wu excelled in physics and eventually moved to the United States for graduate study. By the 1940s, she had become an expert in nuclear physics, known for her precision, discipline, and near-unmatched experimental skill. During World War II, she contributed to the Manhattan Project, working on radiation detection and uranium enrichment. Critical but classified work that few outside the project ever learned about. But her most revolutionary contribution came a decade later. In particle physics, symmetry principles were everywhere. One of them was parity conservation. The idea that the laws of physics do not change if spatial coordinates are inverted, like looking at a system in a mirror. Parity conservation had never been experimentally violated. Because of that, most physicists assumed it was universally true. Two theoretical physicists, Tsung-Dao Lee and Chun-Ning Yang, began to question this assumption. They noticed that parity conservation had never actually been tested in weak nuclear interactions. Their math suggested something radical. Parity might not hold in weak interactions at all. This was an extraordinary claim, and it demanded extraordinary experimental proof. They turned to Chien-Shiung Wu. Wu immediately recognized both the importance and the difficulty of the test. The experiment would require extreme precision, ultra-low temperatures, and careful control of nuclear spin. Wu designed an experiment using Cobalt-60, a radioactive isotope that undergoes beta decay. If parity were conserved, electrons emitted during decay should be distributed symmetrically relative to the nucleus's spin direction. If parity were violated, that symmetry would break. To test this, Wu cooled Cobalt-60 atoms to near absolute zero using liquid helium, aligning their nuclear spins with a strong magnetic field. This alone was a technical achievement. Then she measured the direction of the emitted electrons. The result was unmistakable. More electrons were emitted in one direction than the other. The mirror symmetry was broken. Nature itself preferred a direction. Parity was violated. In 1957, the results were published, and the physics world was stunned. A principle that had been assumed universal was suddenly false. Textbooks had to be rewritten. This single experiment reshaped particle physics and became a cornerstone of the Standard Model. Later that year, Lee and Yang received the Nobel Prize in Physics for the theoretical explanation. Wu did not. This omission sparked controversy that continues to be discussed today. Wu's role was not auxiliary. Without her experimental design, execution, and credibility, the theory would have remained speculation. She continued her research, taught generations of physicists, and became a powerful advocate for women in science. She was known for her blunt honesty and her insistence that science must be grounded in evidence, not assumptions. Wu later received numerous honors, including the Wolf Prize, and became the first woman president of the APS. Chien-Shiung Wu passed away in 1997, but her legacy lives on every time physicists demand proof. Nature doesn't care about elegance or reputation, only about what can be proven. Why are experimentalists still less recognized than theorists?
Science is everywhere if you just know where to look. Thanks for watching SciCurious. Until next time.